I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the AP Physics 1 FRQs from the 2025 exam. This is question 2. In this video, we're going to continue the 2025 AP Physics 1 FRQs. This is question 2 from version J. So in this question, we have a block that's sitting on a ramp that starts at rest when it's at a position of x equals 0. And it gives us three different positions, x equals 0, x equals 60, and x equals 10d. And it tells us that at x equals 8d, that's the moment the block makes contact with the spring and starts to compress it, and that it's completely compressed and at rest when it gets to position of x equals 12d. Gives us some information about the angle of the ramp is theta, and it has a block has a mass m, and there's negligible friction, which means there's not going to be any energy lost in our system. So figure 4 shows an energy bar chart of kinetic and potential energy for the block spring earth system. That's key, block spring earth system. That means all of our energies are going to be in our system. So we are going to draw an energy bar chart for figure 2, which represents the initial position when it's at x equals 0 and not moving, and then also at position 6d when it is moving down the ramp and before it compresses the spring. So what we're going to do is we're going to draw blocks on our energy bar chart representing K, UG, and US to complete our energy diagram in figures 2 and 3. And when the block is released at x equals 0 and when it reaches x equals 60 respectively. And what we need to do is we're going to shade the bars that start on the dashed line that represents 0 energy. We're going to represent any energy that is equal to 0 with a distinct line on the 0 energy line. So we need to make sure that we draw a line that represents 0. You don't want to lose a point for not drawing anything. You got to draw a line that represents 0. And then we want the relative heights of each shaded bar should reflect the magnitude of the respective energies consistent with the scale used in figure 4. So if we look at figure 4, kinetic energy has a height of 7 E naught, UG has a height of 2 E naught, and US has a total of 3 E naught. And if we add those together, it gives us a total of 12. So that means each one of our figures should have a total height of 12. So what we're going to do is we can look and see that at the beginning, it's not moving, and then it has a height that's greater than 0, but the spring is not compressed, which means we have two 0 values. So the energy is all going to be gravitational energy, a total height of 12, but we also have to draw zeros for kinetic energy and stored spring energy. So we draw a line at K and US at 0. Now, when we go to 6D, the spring still is not compressed. So we're going to draw a line on US, so it's still 0. But now it's gone halfway down the ramp because 12D, it told us, is a height of 0. So 6D, it's halfway down the ramp, which means it's lost half of its gravitational energy. So it's going to have a total gravitational energy of 6 E naught. Then when we have a total of 12, that means kinetic energy has to be 6 as well. So here's our energy bar charts for part A, showing the block as it slides down at positions x equals 0, x equals 6d, and then was given as x equals 10d. So now we're going to look at figure 5. It shows that the block at position 0 when the block is released from rest, and the block at x equals 12d when it comes to momentary rest after it compresses the spring. And what we want to do is we're going to start with using conservation of energy. We're going to derive an equation for the spring constant K of the spring using m, theta, d, and any physical constants as appropriate. And we're going to begin by deriving our equation by writing a fundamental physics principle or an equation from the reference information sheet. So what we're going to do is we're going to draw an energy bar chart since we've already been doing that. And we know that at the top, it's not moving and the spring's not compressed, so we can draw 0 for K and US, and we have all gravitational energy. We've already done the x equals 0 position, but we haven't done x equals 12. But what we know is that it's not moving there, so kinetic energy is 0. The height is also 0, so no UG. it has all spring energy. So now we can write our conservation equation where we have gravitational energy is equal to the stored spring potential energy. Now we can look on our reference tables and find the equations for each type of energy. So we end up with mg delta y equals 1/2 kx squared. And that delta y, the change in height, is what we need to represent in terms of theta in d. So if we draw a dashed line and we represent the height that is trying to be found, well, that's just the opposite side of this triangle. So the opposite side is just going to equal the hypotenuse times sine of the angle. So the hypotenuse is going to be a total of 12 and times sine of theta. So we can substitute 12d sine theta in for delta y, and that's going to equal 1/2 kx squared. Well, x starts compressing at 8d, and then it's done compressing at 12d, so it compresses a total of 4d, so that gives us 1/2 k 4d, that quantity squared. Now we just have to go through and simplify. So we'll rearrange 12 mg d sine theta. We'll square 4d to get 16d. And we can see that we have a d on each side, so we're going to cancel out 1 from the left side and just the square part on the right side. And now we can rearrange our equation. So we're going to take half of that 16 to simplify. So we get 12 mg sine theta equals 8 times kd. Then we can solve for k, and we get that k is equal to 12 over 8, which reduces to 3/2 mg sine theta divided by d. And this is the value of the spring constant in terms of our given quantities. We can see that we are allowed to use m, theta, and d in our answer, and physical constants, which is g, so our answer is good in terms of the terms that we are allowed to use. Now for part C, figure 6 shows a graph of the potential energy as a function of position of the block from 8D to 12D. And we have a graph of US that's given for the block spring Earth system as shown. So we have, again, everything's in the system. So on the axis shown in figure 6, we want to do the following. We want to first sketch and label a line or a curve that represents the total mechanical energy of the block spring Earth system as a function of position from 8D to 12D. Well, we know it's the block spring Earth system. There is no change in mechanical energy, and the total mechanical energy is 12. So we're going to have a horizontal line, and we're going to label that E as it told us to. We had to sketch and label, so don't forget to label your graphs as well. The second part says to, again, sketch and label a line or a curve that represents the gravitational potential energy, UG. So we're going to label our graph UG for the, again, the block spring Earth system as a function of position for the block from 8D to 12D. Well, we know at 8D, it has a height that is equivalent to an energy of 4 E naught. When it gets to a position of 12D, we end up with 0 gravitational energy. And if we look at our equation, UG equals mg delta y and UG are directly proportional, which means that this graph is going to be a linear function. So we draw our graph and label it UG. So this is our graph of total energy being constant, and the gravitational energy decreases linearly as a function of position. Now we want to indicate whether the speed v90 of the block at x equals 90 is greater than, less than, or equal to the speed at position 8. So we want to justify by using our graph from part C. So if we look at our graph from part C, we have an energy bar chart. We're going to draw our bar chart, and we can see that we have a height of 4 E naught, a gravitational energy of 4 E naught. We have no spring energy, so we can draw 0, which means if we've got 4 E naught, that means we've got a kinetic energy of 8 E naught as a total of 12 for our energy. Then if we look at position of 9D, you can see that the gravitational energy is at 3 E naught. The spring energy is just a little bit below 1, which means that the kinetic energy has a slight increase to be just a little bit bigger than 8 E naught. So what that tells us is that there's a little increase in kinetic energy. So since the total potential energy at 8D is equal to 4 E naught, and the total potential energy at 9D is less than 4 E naught, that means the kinetic energy had to increase a little bit, which means if kinetic energy at 8D is less than kinetic energy at 9D, That means the velocity at 8d is less than the velocity at 9d. So we've checked the box that says velocity 9d is greater than 8d. Now, looking at the graph, if your line did not cross exactly and you ended up with a potential energy of 4 for both situations, the scoring response will probably say consistent with the graph drawn in part C. So if your graph in part C shows at 90 a total energy of 4e naught for potential energy, then you will probably get full credit for that because you referenced it correctly. So this is why it's important to use that straight edge to use a ruler to draw your graph and connect those lines so you can see that they go through straight from 4e naught to 3e naught, 2e naught, 1e naught to 0e naught, from 8d to 12d. So this is free response question 2 on the 2025 AP Physics 1 exam. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, and subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.